Okay, so we are continuing with the topic of solution of state equation systems by Laplace transformation. So we will deal with this topic through this example. Assume that I have this circuit, series RLC circuit, which is characterized by, as you see, state equation system. Two initial conditions are provided. So for a mathematician, this is the full set of information required for the solution. So a mathematician can handle the rest of the solution by processing this box. Okay. So one of our goals is formalizing this circuit in terms of state equation, that is, writing the contents of this box. Next, how I can get the solution. Okay. So what do I mean by the solution? I would like to satisfy this differential equation, first order matrix differential equation, and also the given initial conditions. So we will be applying Laplace transformation for the solution. So what is the central result? The central result is the following. If Laplace transformation of f of t is f of s, okay, then Laplace transform its derivative f dot of t is equal to s times f of s minus f 0 minus. This is a remarkable result in the sense that in time domain I have a function and its Laplace domain representation is f of s. So I process this function in time domain by derivative operator. I get this. So we see that the equivalent operation in the Laplace domain is multiplication by s and subtraction a scalar. A scalar is essentially the initial condition. So which one is easier? So you see that multiplication by this s variable is rather easy than differentiation. So we'll be making use of this fact for the solution of state equations. So let me keep this. Okay. So if I focus on this first equation, so what does it say? Laplace transform of, let me check, is this correct? Laplace transform of Vc of t dot is exactly like this, is equal to Laplace transform of, what do I have on the right hand side? 1 over c il of t, isn't it? That is it. So if I take the Laplace transform of my, let's say, first equation, what do I get? Well, so number one, after Laplace transformation, okay, so this will be s times Vc of s, okay, minus Vc 0 minus, which is this initial condition, is equal to right hand side's Laplace transformation. On the right hand side I have Laplace transform of 1 over c times il of t. Okay, so let me use small letters for this one also. So this will be il of s. Okay, that is it. So I can handle the second equation also, but instead of doing it like scalar equation, let's use our matrix information and let's try to deal with this equation system using matrices. Okay, so this will be something very natural to you eventually. So I will rewrite this as follows. State vector derivative, state vectors linear combination plus b times, there is a single input, this. Okay. So I am given 0 minus values of the solution as a fixed vector over here. Now I would like to take the Laplace transform of this equation. So how do I handle this? So what's the meaning of this? So I'll be taking the Laplace transform of this first element and then the second element and write them in matrix form. This is what we have done a few seconds ago. So if I do that, I'll be multiplying the following: s times x of s minus the initial condition of Vc and il should be subtracted, but in vector form, but that's already given to us, minus x naught, isn't it? That becomes the Laplace transform of essentially this part. x dot of t. Okay. So how about this? This is simply a matrix times the state vector. So it would be a linear operation then. So Laplace transform of first one, as we have written, is just this plus that. This one will be summation of these two. So the coefficients are given in the matrix essentially. Very good. So I'm handling, as you see, both equations at the same time. So I have B, and let me write capital letters, Bs of s, like that. Okay. So there are some details, like how do you take the Laplace transform, equality of left-hand side and right-hand side for all, let's say, t greater than 0, and so on. Now I should be getting the solution in Laplace domain by processing this, isn't it? So how can I do that? Again, we did this a few times. So what did we do? Well, I have included an identity matrix over here. Okay. It doesn't do anything for this multiplication. S is the scalar, Laplace domain variable, identity matrix, times the state vector in Laplace domain. Now I move this to the other side, to the left side. Now I am combining x of s, this vector, and pulling all the terms that are factors of x of s, and collecting the common terms from right, as you see. So s times identity minus a, so this term is this one, this term is this one. I put x naught over here, and done. So I need to solve this then. Okay. So how do I handle this? Now, since s is a generic variable, I can write this as plus si, let me write s a little better, minus a inverse b times vs of s. Okay. So this is, you may say, my complete solution. This is the end. Complete solution in Laplace domain. Okay. So what do I mean by complete solution in Laplace domain? There is nothing else to do. In Laplace domain, I got x of s. So if I can take the inverse Laplace transformation, now please see this. This is Laplace transform of, this is what I have found, x of s is the Laplace transform of this vector. Obviously, my state vector. Okay. So the first element of it is Vc of s, the second element of it is Il of s. So this is a two-element vector. This is a two-element vector. This is a matrix, but it contains s as a variable, as you see. Similarly, this is the same matrix. This is b vector over here, and Vs of s is our input in, this is the input, obviously, in Laplace domain. Okay. Inputs representation in Laplace domain. So let's do some numerical calculations then with this result. So let me fix some RLC values. So let L is equal to 1 Henry, R is equal to 6 ohm, C is equal to 4 over 100 farads. Okay. And then, okay, let's try to write this. Then x of s, my complete solution, is equal to Si minus A inverse. So let me try to write that matrix. Si, so S is this. Okay. Minus A, so this is A. So this is, up to now I have written this part, S times identity. Now I'm subtracting A, okay, minus 0, minus 1 over C, plus 1 over L, plus R over L. So I should take the inverse of this, and then multiply by initial condition vector, which is the first state element is capacitor V0, I0. V0, I0, okay? And then I do the same thing, the same matrix. There is this B vector, 0, 1 over L, and Vs of S, okay? So what are the numerical values? Well, C is equal to 4 over 100, 1 over C is, so I have minus 25 over here. So this is equal to 1. Okay. R over L is equal to 6. Okay. I have something like this. 1 over L is equal to 1. Well, this is the same matrix. Let me write same. Okay. Now I should take the inverse of this matrix. So I will do this, 1 over delta. Okay. So I exchange these two places, S plus 6, S, alter the signs of these off-diagonal terms. Minus 1, V0, I0. Okay. So what is this delta? Delta is the determinant of this original matrix, okay? That I'm inverting. So I'm inverting Si minus A. So its determinant is S times S plus 6 plus 25. Okay. So let me write it a little further. S squared plus 6S plus 25. Or I can write this as S plus 3 parentheses square, since we have done this before. I'm doing a little fast. Plus, there's a 9 over here. I need 25, 16. Okay. So what do we see? This has, which will be the, our natural frequencies eventually. We have complex valued natural frequencies because this doesn't have any real roots. Okay. So very good. So this is that matrix plus, well, let me write the same thing, the same matrix over here. Let me do not forget what 1 over delta, and I have 0, 1 and Vs of S. That is the end. Okay. So how can I? Well, let me try to write this matrix. Then, because it's appearing at two places, a little bit bigger. So what are its elements? So I have S plus 6 divided by S plus 3 square plus 16 square. 25 S plus 3 square plus 16 square because of this. This is, I think, S, not 5. S plus 3 square plus 16 square. Okay. And I have over here minus 1. Is this correct? Minus 1. 16. Okay, that is that matrix. Okay, so this matrix times the initial condition plus this matrix times this part will be my complete solution. So how about this? Okay, one thing to notice. Now, would you say that this part of my solution, this part, corresponds to the zero input solution? So what do I mean by the zero input solution? So this part is zero input solution. The reason is when the input is equal to 0, then whatever remains is the zero input solution. Since this is always the complete solution, so this part is the zero input solution then. Observation number 1. Now a related observation, let's use another color, than this part. This should be the zero state solution, am I right? ZS. Zero state solution in Laplace domain, red one. Why? Zero state means that initial conditions are equal to 0, capacitor uncharged, There is no flux initially. Okay. Then these two are equal to 0. If those are equal to 0, you are left with this part of the solution. This is obviously related with the input. It's a function of the input in Laplace domain. So this has to be the zero-state solution. I mean, very nice, ZS. ZS means state variables are equal to 0, zero-state variables. Okay. So let me do this. So let's focus on the zero input solution then. So how can I focus on the zero input solution? Well, it is then this matrix times V naught I naught. Am I right? So then let me move this. I think we don't need this sentence. This says that, here you go, zero input solution. So if you wish, I can write with green to be compatible with the colors. It is this green part. Okay. Now, can I get the zero input solution in time domain then? So I should take inverse Laplace of this. Or let me do it this way. Laplace inverse. So then I'll be getting x zero input in time. Maybe I need more space. So then let me write it smaller. Because I may need more space. So this is V naught, I naught, and so on. Okay. So how can I take the inverse Laplace of this? Okay. That is the issue. So let's start with this one. So if I put this term, if I put 4 and 1 over 4 over here, which is 1, and if I combine then these two, okay, so this becomes immediately 25 over 4 e to the minus 3t times, this is sine 4t. Let's do not forget ut, there is ut present over there. Okay. Very good. So how about this one? This is almost like the same by linearity. I can say that this would be, I need to divide this thing by minus 25 and I will get this, okay, whatever I get. So this minus 1 over 4 e to the minus 3t sine 4t ut. Okay. So how about for this one? This one I can write s plus 3, put a bracket, and minus 3 like that. Okay. Now this term will be the first one, s plus 3. Now this will be e to the minus 3 cosine 4t ut. So on this part. Okay. How about this? Then this is the negative minus 1. If you multiply this one by 3, is it 3 only? It's just 3 only. So I need to multiply this one by 3 plus minus 3 over 4 e to the minus 3t sine 4t ut. Okay. How about this one? This one is, let me write this 6 then, or let me write this 6 as 3 plus 3. Okay. So it's almost like this then, except this is with different sign. So I copy it from here. E to the minus 3. Of course, I mean, this is a simple calculation. Just I'm using my earlier results. And I'm hoping that I'm not propagating any errors. Because if I have an error at some point, it's just repeated everywhere. You just have to be a little careful. But as you see, this is an easy result. Okay. So that is it. So what is the zero input solution? Then the zero input solution is this matrix times the initial condition. Zero input solution. Okay. So do you remember this? So previously we have defined something called state transition diagram. Okay. So let's remember what that was as. So I have phi, this is a matrix T0. Okay. This was called state transition diagram. So it transits or transfers state transition, sorry, this is not a diagram, this is a matrix. Okay. State transition matrix. Okay. So we have this initial state of the capacitor and the inductor. So if you multiply it by this matrix that we have found, you get the state at another time, at a later time actually. Okay? Because everything has t greater than 0 dependence, UTs everywhere and so on. Okay. So very nice. For example, how can I check this? If my calculation is correct, when t is equal to 0, this should be an identity matrix, isn't it? Because there is nothing to transfer. When t is equal to 0, well, I have 1 over here. This is 0, 1. Okay, it's an identity matrix. At least it satisfies that. Okay, I'm happy about that. Of course, this is not a, this is just a necessary condition. I mean, it should be, it doesn't say that this is correct, because I have just seen that this is equal to 0, this is equal to 1, this is equal to 1, this is equal to 0, this is equal to 0 at only a specific time. But if my Laplace domain result is correct, then my inverse Laplace domain result should be correct. Then this matrix should be identical to the state transition matrix that we have found earlier. So how do we find this then? So previously we were finding this by eigenvectors, you may remember. But right now, in Laplace domain, I can say that this matrix is inverse Laplace of Si minus A, like this calculation. Si minus A inverses this matrix, so I have written it bigger and so on. So if you take its inverse Laplace of every element of it, then you get this state transition matrix. So another notation for this is e to the at, okay, or I should write t minus 0, but I mean A is a matrix. This is, you may consider this for now just a notation, e to the at. A is a matrix and so on. So this is just another way of writing this phi or state transition matrix. So the notation is it transfers the state from 0 to t, okay, something like that. So that is the end. But how about, you may wonder, the zero state? So how can I find the zero state response? So the zero state responses, so then let's focus on zero state response. So how can I find the zero state response? Well, it is actually the following. Let's copy it over here. Zero state is in Laplace domain. It is this, Si minus A inverse, okay. Do I have inverse over here? I should put inverse, times B times Vs of S, okay. So this should be the same as you see over here. Now, how can I handle this? So let's look at this impulse response. Let Vs of t be delta t, then x Zs of t will be x impulse, not t, but right now we are in S domain, S, okay. So I have Si minus A times B times Laplace transform of impulse. The reason I have selected impulses, because impulse's Laplace transform is just 1, okay. So let me write over here then just 1 Laplace transform of my input, okay, delta t. Well, how can I take, well, in time domain then? I think we know what to do. So this becomes the impulse response then. Okay, this becomes the impulse response in time domain for t greater than 0. Well, let's pay attention. In our notation, we have UTs everywhere in this matrix. So this matrix is defined for t greater than 0. Okay. So why do I have so? Well, this is exactly the same calculation. So Si minus A inverse times the initial condition. Okay, it was zero input solution. Now for the zero state solution, I should calculate the same thing, but instead of this, initial condition, first of all, I have this B vector and the Laplace transform of the input. But when the input is in Laplace domain is equal to 1, just B vector. So it is as if this initial condition is replaced by this B vector. Okay. So this is the impulse response. Now, how about this then? So this is the impulse response. The first element will be the impulse response for the Vc of t. The second element will be the impulse response for IL of t in our example. Now, how about this? Let Vs of t is 5 delta t minus 6 delta t minus 2. So can I find this zero state response for this input? Okay. So from our earlier information, well, we say that this is equal to essentially the linearity of this zero state responses. So impulse generates this. So this is 5 times impulse. And then minus 6, this is due to linearity. Minus 6 plus addition, and this is t minus 2. Due to the time invariance, this will be just a shifted version of it. Okay. So linearity and time invariances, both of them are needed over here. So the nice thing is that, well, I know what to do. I can write this matrix times B minus 6 phi. Instead of t, I'm writing t minus 2 B and so on. So if you have this matrix, replace wherever you see t by t minus 2. For example, here is a t, here is another t, here is another t. Okay. So this is the argument. Okay. So you replace this t argument by another argument, t minus 2. Essentially, this delays the response 2 seconds to the right. Okay. Where the second impulse is located. Okay, so this is very good. So I can write the solution for, let's say, superposition of impulses. So how can I write this in more general form? Now I can maybe generalize this idea. Then, how about this? Vs of t. Let's assume that I have many impulses then. Okay. So what is this? Well, Vs of t is equal to something more complicated, you may say. But if I apply the rules of, Dirac delta calculation, what is this? So for the sake of this integration, t is something fixed. T is integration with respect to tau, as you see. Okay. For the sake of that calculation, t is just a constant quantity. Okay. Now, this product, as tau changes, because t is fixed, as I have said, is equal to 0 unless this tau is equal to this already fixed quantity. So this would be equal to then at this time where the impulse is located when tau is equal to t equal to this. Again, this will be detailed discussed in some other courses also, in 301 courses, in signal processing courses, etc. Now you can take this out, okay? And then, since I'm always focused on what happens after the initial condition, t greater than 0, so you're integrating an impulse located in this interval, because this impulse location is at time t, when this argument is equal to 0. So this is a positive argument, so this is equal to Vs of t is equal to Vs of t. Okay? So there is nothing fancy about this. But as you see, this generalizes the idea of having, two impulses, two continuum of impulses. So for example, if I have an impulse at t is equal to 0, tau is equal to 0, its weight is 5, then tau is equal to 2, its weight is minus 6. Now you see that this impulse is located at t, okay, it's located at t is equal to 2, weight is 6. If this impulse is located at t, okay, its weight is this number, okay, that is it. Well, let me erase this. Okay, so this is Vs of t. Now, if my input is composed like that, again, the same reasoning. Now, the zero state solution is then, let me write it over here. 0 minus to infinity, Vs of tau, okay? So what is this? Response of my system at a delayed impulse. So this would be equal to impulse response at t minus tau, the same reasoning. Okay. D tau. So let's erase this. So let's go over here then. Vs of tau. How about this one? This is equal to this. Phi t minus tau 0. There is b. Okay. And there should be d tau. Okay. So you can right now use this notation if you wish. For this one, you can write this as e to the a t minus tau for this one. Okay. Now, one more thing. This thing has u of t everywhere, isn't it? This matrix says, this is my, as you see, phi matrix. This is our phi 0 matrix, is this. So it has u of t at every entry of it. So let me write also this u of t over here. I mean, it doesn't do anything but I should write after t minus tau substitution, something like that. D tau. Actually, we are accomplishing something, I guess, because we are doing some, time domain calculations right now. So this should be my result. So one last thing. So as tau ranges from 0 minus to infinity, this u of t gives 1, provided that this argument is positive valued. Okay. So t is fixed. T is just fixed time, let's say. So if tau is in between 0 and t, this is 1. But if tau is greater than t, this becomes negative, as you see. So you can see that, while this u of t, or this matrix essentially, the u of t is in this matrix, is limiting this to upper, let me write it again then, 0 minus to t. Let me change this then. Phi t minus tau 0 b Vs of tau d tau. Okay. So this becomes the zero state solution. Again, this is rather a technical result, but what we see is that the state transition matrix present over here, an arbitrary input present over here. Of course, if my input is composed of such a thing, 5 delta t, and so on. So this will be 5 delta tau minus 6 delta t minus 2. Okay? Then you get this. In other words, for this one, you are writing, let's apply this one first. 5 times delta tau. So you are writing instead of tau 0, you get this. Okay? So when you insert this, minus 6 is present, t minus 2, you have delta t minus 2 over here. Okay? Tau minus 2 over there. When tau is equal to 2, now you have t minus 2, 0 over there. You take it out, and area under the impulse is 1. You exactly get the same result. Okay? So this is the nice thing about impulses. So these simple ideas also extend to continuums, and you get, this general result for the zero state solution also. So one thing, well, this u of t was critical in this calculation. Please do not forget these u of t's, because with the help of that u of t, we have managed to correct this upper integration limit, okay, to this. So let me give you one more example about the importance of that u of t. This may confuse you a little bit. I think it will be, somewhat like leaving you let's say, an imprint in your memory not to make similar mistakes. For example, when I was a student, I was thinking that if I know this, let's say that I know this, the question is, how do you find, Laplace transform of cosine omega t? Okay, not giving too much details. Now you say that, okay, Laplace transform of cosine omega t ut, okay, is, well, I can calculate this, but just we have seen the utility of this derivative operator. So if I take the derivative of this argument, sine gives me cosine, but there is an additional omega over here. Okay. Now, if I apply this derivative rule over there, so derivative rule tells me that s times, I should multiply this thing by s, times omega. So this is the effect of derivative in the Laplace domain, as you see. So I put an omega over here, minus, now this thing, but because of u of t, as you see, I should be subtracting 0, isn't it? So is this correct? Yes, indeed it is correct, because there is cancellation of this, you get the Laplace transform of cosine. When I was a student, I have figured out this, and I was happy. Okay? So I have made use of these earlier results, and I get a consistent result for the Laplace transform of cosine. This is very good. Now, let's do the other one. So let's say that I have Laplace transform of cosine omega t ut. Let's say that somebody has given me this. And the question is, as you can imagine, what is the Laplace transform of, how can you derive this? Laplace transform of sine omega t ut. Okay, so I want to find this. Again, I know this derivative rule. If you differentiate, time differentiate this, what do I get? Cosine's derivative is first of all minus sine, and there is minus omega then coming over here. You may say it like that. Then this corresponds to s times, again minus 0, because this thing is u of t present over here. So what's wrong? So I get you see what I mean? This is not good, because I get s squared over here. I'm not getting the right answer. The answer should be this, obviously. So the true result is this. So where is mistake over here? So this was puzzling me, because I have tried to do my best, applied this. So this is the equivalent operation of derivative in Laplace domain, but I'm not getting the right answer. So where is the mistake? So the mistake is this differentiation. Okay. So what do I mean by this differentiation? So let me erase this. Okay. So if you differentiate this, you should be doing this. This is first function number 1, function number 2. So if you differentiate it, function number 1 derivative times function number 2. Function number 1 times function number 2 derivative, am I right? Should be calculated. This was my mistake, because this is product of two functions. You can say that we didn't do such a thing over here, but I think it will be clear. So this should be equal to, this differentiation should be equal to this right-hand side, because I did this differentiation wrong essentially. So let's see. If this is this, then s times this, I'm writing this one, minus 0. So I was calculating the derivative wrong. Okay? So if we go this way, then, so this is the Laplace transform of first function's derivative is, actually it is this, minus omega sine omega t ut, okay, f2, plus f1. Second function's derivative is, ut has a derivative of delta t, okay, so let me write, let's match the colors. This is supposed to be equal to, for consistency, I should have that, minus 0, okay. So, how about this? Again, this is equal to, this function evaluated at Dirac delta's location. I get, this is when t is equal to 0, this is equal to 1. So this is just delta of t times 1, okay. So then, Laplace transform of minus omega sine omega ut is equal to Laplace transform of 1, or not 1, sorry, delta of t is equal to s squared plus omega squared. Okay? So this is equal to 1, and if I move this one to the other side, let me do this then. Let me erase this. This is then minus 1. I have a plus sign over here. Okay. Now, if I equate this, I get omega square, s squared plus omega squared. Okay. There's a minus sign also. And then, now this part is equal to this part, which is indeed the result that I like, because this would be cancelling one of these, so this will be my answer. So you see that, well, my mistake was at the least expected place, isn't it? Because I didn't pay my respects to this u of t's presence over here. I was treating that u of t as like a piecewise definition, but do not do it. If you are dealing with, generalized functions, u of t, Dirac delta, and so on, these properties, differentiation properties, etc., they are valid for these generalized functions, Dirac delta, unit step, and so on. So you should be, taking derivatives if required using this u of t. So this is the reason that these u of t's are rather important. Okay, that can give you some difficulties. So what happened with this one? So why this was correct? Well, if you take a derivative of this, first function, second function, if you do this calculation, first function's derivative is this, second function is this. Now first function itself is sine, derivative of u of t is delta t. So sine omega t times delta t, but sine omega t takes the value of 0 over here. So this is 0 delta t. So by chance, the second term was 0 over here if you take the derivative. By chance this was correct. Okay? Even though I have differentiated wrongly, in other words, this should be sine omega t. So this should be included. But since this is equal to 0 times delta t, this is equal to 0, I don't get any inconsistent results. Okay. Okay, that is all. So what we have learned? Actually, we have learned quite important things. So this is a state transition matrix. We have previously calculated the state transition matrix using eigenvalues, eigenvectors, etc. for diagonalizable matrices. So this, right now we have a new method. I can calculate this in Laplace domain through this general method this. So this is my preferred, you may say, state transition matrix calculation via Laplace transform, as you see. So Si minus A, this is the matrix coming up in the solution of state equation system. Inverse is calculated, and then you take the Laplace transform inverse Laplace of entries of this matrix, and you get the state transition matrix. Once you have the state transition matrix, you get the zero input solution. So what is the zero input solution? Very simple. Initial condition, state at t is equal to 0, multiplied by the very nice name, state transition matrix, you get the state at a future time. Okay. So how about the zero state solution? Zero state solution is essentially the same idea, but if you think in terms of impulses. So if you have a bunch of impulses over here, you are adding up the impulse response of all of them individually through this calculation. If you have a continuum, arbitrary function, written like that, Vs of t, then you can do this integration, you are done. Again, in this calculation, this is a matrix, this is a vector, this is just a scalar function, our input Vs of t function. Now you have a vector if you do this calculation in the integrand. Now you integrate that vector from 0 minus to t, you get your final result. Okay, that's all for the solution of state equation systems. See you next time.